Hello, everyone, and welcome back to our regular webinars here at IBM Research, where we share with the world, with you guys watching us right now, all our latest milestones, breakthroughs, discoveries. I'm Katya Moskowicz, the editorial lead of IBM Research, and as usual, I am here at IBM Research Lab in Zurich, Switzerland. The topic today is quite exciting and also, I would say, quite important, right, for many of us. It's energy. I don't think there are many people out there who don't care about energy storage, energy production, the cost of energy, and so on. I mean, think about it, right? Like if you're a kid, of course you would care about your, remotely controlled car to last longer, right? It's like you don't want to just keep running to your parents begging for new batteries. And if you're an adult, then you probably, to some, like many of us, care about sustainability, using renewable energy, which means better energy storage solutions, of course. And we all care about the cost of electricity, cost of energy. So energy for many of us is quite a crucial topic right now. And this is exactly where quantum computing, this super awesome next generation technology inspired by nature, can really help. And of course, next to me, I have a model of a quantum computer, and I hope that at least some of you have, watched our previous webinars on quantum computing, where we explain quite in detail what quantum computers actually do. If you haven't, then please do go back to our earlier webinars, especially the one I did in February with my colleague here in Zurich, our quantum lead, Heike Riel. She's amazing, and she explains really well and in great detail how this amazing machine actually works. So do go back and watch, but not now, of course. Do keep watching us right now for another hour. And we also going to be talking about AI, artificial intelligence, so how quantum and AI can help us build the next generation battery of the future. Before we go to our two presenters here, though, let me remind all our viewers to please send us your questions in the YouTube chat, because behind the scenes we've got an amazing team of scientists who will be answering your questions in real time. A lot of the questions we will also answer live, of course. They will be sent to me, and I will be then asking our presenters. So without further ado, let me introduce our amazing presenters today. All the way from California, joining us, Gavin Jones, a chemist who uses quantum computers to run molecular simulations. And we will talk about what exactly that means more in detail during the show, and Gavin will tell you all about it. And here in Zurich, joining us, computational chemist Teodoro Laino, who has been looking into creating better batteries for electric cars for a few years now. Today, he's actually working on accelerating the discovery of new materials, including materials for energy applications. Welcome, guys. Thank you for joining us here today.
Ciao, Katja, and good afternoon, good morning, good evening to everybody.
Hello, everyone. Thanks for joining in.
So the first question from me is for you, Gavin. And again, just to encourage our viewers here to start sending questions in the chat. But the first question is going to be from me. Please tell us, what is actually this connection between quantum computing and batteries in a nutshell? Like if you can just explain how quantum specifically could help with battery applications.
Sure. Well, I'll talk briefly about quantum computing, since there may be viewers who are not familiar with quantum computing. Then I'll talk about quantum computing and chemistry, and then specifically batteries. So quantum computing is a new form of computing in which, instead of using bits comprising 0 or 1 as a basic element of computation, we use qubits, which comprise superpositions of 0 and 1, meaning that it's a combination of 0 and 1 at the same time. And the significance of this is that you can potentially represent more states with a quantum computer than you can with a classical computer. One other useful property of quantum computing besides superposition is entanglement, in which qubits interact in a way such that the quantum state of each qubit cannot be described independently of the others, even when separated by a large distance, which means that whatever is done to one qubit happens to the other qubit. So this is one of the fundamental differences between a classical computer, like your laptop or a supercomputer, for example, and a quantum computer. We also use quantum logic gates in quantum computing that are similar to classical logic gates, like the AND or NOT gates. Some examples are the Pauli X and C NOT gate, represent the unitary operations of these quantum gates on qubits as rotations around a Bloch sphere. And combinations of quantum gates can perform operations on qubits, which are composed into quantum circuits, similar to how one would compose a classical circuit using classical gates. Now, moving on to quantum computing and chemistry, chemistry is one of the near-term applications of quantum computing. One of the reasons for this is that it's better to use a quantum computer that has quantum properties to perform computations in a quantum system. And the reason why we perform simulations is to understand physical problems, of course, to create new theories, to explain these problems, and to predict what will happen if similar problems are repeated, and to also explain unexpected results. Computational chemistry is a large field. For most of the talk, I'll be talking about quantum chemistry in particular, in which researchers are trying to model atomic interactions as accurately as possible using the Schrödinger equation. Now, the energy sector is one of the important sectors of chemistry that we believe will be impacted by quantum computing because the world's demand for energy is growing at a dramatic pace. More research is needed to discover alternative energy sources, including batteries. And to cut the story short, we believe that quantum computing could play a pivotal role in this space because it may be possible for quantum computing to enhance the types of simulations that we can perform on some of the processes that occur in batteries because they are really complex, complicated processes that classical computers cannot really deal with at the moment. So we believe that quantum computing could improve our ability to make more accurate predictions.
Right, and if I understand correctly, it's mostly about, or at least in part about, better simulating molecules, right? Because we, like, obviously to create a new material, we first need to create a new molecule, and to create a new molecule, you have to have this configuration of atoms arranged in a specific way, right? And is that if you can explain, like, from because you're obviously the chemistry expert, how exactly it works? Like, how can you find this perfect molecule for your new material, and why quantum computers are better in that task than classical ones?
Well, I mentioned quantum chemistry, and I will grossly understate things by saying that it's very complicated. There are many types of simulations that we can perform.
I mean, even normal chemistry is quite complicated, right?
Yes, it's very complicated as well. Quantum chemistry is just another order of computation above that. So there are many types of simulations that we can perform, and we can obtain answers that will allow us to make assumptions based on the results that we generate. Can form hypotheses, we can innovate based on these hypotheses. But quantum chemistry as practiced today on classical computers also struggles with many problems. And this has mostly to do with the accuracy of the quantum chemistry methods and how easily we can actually carry out these simulations. For example, one of the most widely used methods that we use is density functional theory, or DFT. But we have to carefully evaluate the accuracy of DFT methods by benchmarking. And this is time consuming. And there's no really reliable way to improve your results. In addition, some methods may not accurately simulate chemical species with exotic electronic structures, such as radicals, biradicals, and so on, with unpaired electrons. And these are normally generated in batteries. DFT methods are not universally accurate. In order to characterize the electronic structures of these species, we like to use more accurate methods, such as wave function methods, to study these types of systems, but they can be very expensive in terms of the memory required, the amount of space required, the amount of time required for the computation. And we believe that quantum computing could help us by allowing us to perform such types of electronic structure calculations or wave function calculations more efficiently.
Mm-hmm, mm-hmm. Yeah, that's a great explanation. Thank you for that, Gavin. And of course, as you mentioned, all these simulations are super important for new materials, and in our for our discussion today, for new batteries, right? And with that, let me go to Theo now. And Theo, what's your view? Why do we need new batteries? I mean, Gavin kind of touched upon that already, obviously, but I would really love to hear what you think. Why is it that you guys are actually working so hard to create new batteries for the world? I mean, we already have batteries, right?
Sure. But the reality is that we need really for different reasons, and one of the I think the most important one that may not necessarily be of relevance for electrical mobility is the fact that we need battery technology that is also capable of absorbing the energy that is produced with the sustainable renewable sources. These are very fluctuating sources of energy. The sun one day shines, the other day it's cloudy, you have strong winds one day and no winds for a week. And we need to be able to absorb that energy and store it for when the society really needs it. On the other hand, we need to, if we now look more at the consumer good market, like electrical mobility, it's crucially important to push the technology to, let's say, advance more and more the experience of driving an electric car. We know that, I mean, there are different reasons for that, of course. I mean, one is also when I started working on the battery fields, and Katya, this goes back a little bit of times ago, like 12 years ago. We initiated a project at IBM that was called Battery 500, and we really put lots of effort in exploring new technologies, mostly metal air batteries that may have been actually very good candidate for creating that gap that would have really provided more value and a better experience for people driving electrical mobility. And of course, you do that for different reasons. I mean, one is the primary experience of a person driving a car and not having the anxiety of thinking that the battery is going to discharge quickly and you will be in the middle of nowhere. So basically elongate the range. But we also need to do that for other reasons, because there are so many other sectors. As I said, electrical mobility is a very important one. It's one that I do care personally. So I'm a strong supporter of electrical mobility. But if we think to other types of technologies, like even semiconductor technologies, there have been very fascinating projects even within IBM, where we were trying to understand whether the replacement of specific wiring inside the semiconductor may have been possible through the use of specific liquids. At the time, we were talking about electric bulb. An electric bulb is nothing more than a liquid that is carrying out electricity and then using a concept which is very similar to the concept of a battery, extracting the energy out of the fluid for powering the electronics. So I think, I mean, there are so many levels in our society, from consumer goods to infrastructure works, thinking to stabilization of grid and storage of renewable sources, but even all the way to miniaturization and semiconductor, where the further development for battery materials is something that we cannot ignore anymore.
Mm-hmm, mm-hmm. Yeah, I mean, I totally agree. We can't ignore it for sure. And also for IBM specifically, it's such a huge topic, right? A huge field of research that I think last year we even had it on our 5 and 5 list of predictions. So prediction that we think is going to come true within the next 5 years. Is that right, yeah?
Absolutely. The energy was one of the 5 predictions, and For people that may not be aware what is 5 in 5, and maybe I may also ask the colleagues if they want to paste the link of the 5 in 5 of 2020. It's a bet that we do as IBM research on technology, on fields of technology, where in the next 5 years there will be a revolution. And last year it was about materials. Materials that may have had an impact on technologies that are relevant for sustainable goals. I loved a lot 2020, irrespective of the pandemic and all the situations that happened worldwide, because it was the year for the UN Sustainable Goals. And so we had really a very strong drive, even in analyzing the patterns and identifying the 5 main themes where the development of novel materials may dramatically change the technology, the situation of the technology, and energy is there. And energy was there as development of materials for batteries.
Cool. Yeah, absolutely. Thanks for that. And we now have questions coming in actually from the audience, and there is one for Gavin. So somebody here is asking, looks like if any one of us wanted to actually simulate chemical reactions in batteries using the IBM quantum tools right now, what are the current IBM quantum computers actually capable of? Gavin.
Sure. As I mentioned, most of the efforts in quantum simulations for chemistry has been on using quantum chemistry. We have had some degree of success, but there's still a lot of work to do. So we've developed several error mitigation techniques, such as those designed to deal with device readout error, those to perform noise extrapolations, and so on. We've also developed strategies to reduce the number of qubits required to simulate larger molecules. For example, exploiting symmetry, use of frozen cores, use of active spaces for reactions. We have created nuance sets that can be used to actually do these simulations on quantum simulators as well as on quantum hardware. We've created we've used near-term variational algorithms such as VQE, or Variational Quantum Eigensolver, to perform hybrid simulations, partly done on classical hardware and partly done on quantum hardware or with quantum simulators. But there are many challenges, and these mainly have to do with the development of better quantum algorithms, development of better hardware. Some of the main challenges are that we need to develop and use better quantum algorithms, as I mentioned. At present, because we have a limited number of noisy qubits, we're dependent on quantum algorithms like VQE, in which you run a quantum circuit hundreds, if not thousands of times in order to perform statistics and obtain a final energy. There are other algorithms that have been developed for chemistry, like phase estimation, but they require too many qubits, or they require the ability to operate on deep quantum circuits, which is not something that we're capable of doing today. We have a limited number of noisy qubits, but because of this limitation, we try to limit the number of qubits that we're actually using as much as possible, because the error increases while increasing the number of qubits that you're using. So at present, we can only perform calculations on small chemical systems, or we study systems in which we limit the number of orbitals being used in order to map onto fewer qubits. We also limit the size of the basis set, which describe the atomic orbitals, to a limited set in order to reduce the number of qubits and gates needed. So in general, the development of better quantum hardware and error mitigation techniques, or fully fault-tolerant qubits, would help. Right now, we interface with quantum computers in the cloud. In the future, we hope that quantum computing would work right alongside classical computing for chemistry problems, so that it would be even easier for us to actually use the quantum computers that we have.
Cool. By the way, I can't help but comment. you're talking about all this super cool futuristic stuff, and you're joining us from your bedroom, which is quite amazing. But it's such a norm right now, right? It's like people are just working from home, and even if you're working on quantum applications and really amazing stuff, as you mentioned, through the cloud, of course, so you can access your quantum computers through the cloud. You don't have to actually be anywhere else right now, right?
Right.
What you were just talking about right now, actually, you kind of answered the question that's been sent to me now for you from Ayu Zhang, who is asking, the current quantum computer is still NISQ. How to apply this kind of device with limited size and error to real applications? So maybe you could just summarize, well, first of all, what NISQ is, but you kind of answered that already, but maybe just to simplify a little bit for the audience who are maybe not so don't have so much expertise in quantum computing terminology.
Yes. So NISQ stands for this refers to these near-term computers that we're using today. So these are quantum computers that are limited in number of qubits and are also noisy. And as Kelly mentioned, yes, I did answer a lot of this already. So we've tried to implement a lot of techniques to deal with the noise that we have. We try to limit the number of qubits. We try to develop error mitigation techniques and use them while we're doing all these simulations in order to more accurately simulate the systems that we're interested in.
Great. And as we mentioned earlier, right? So and you keep repeating it. So we are using these quantum computers for molecular simulations. And we will be using them, more in the future when they will be working better than classical ones, specifically for molecular simulations to create better materials and hopefully better batteries in our case. But at the moment, we are not quite there yet. So today we have to rely on today's technology, right? And now with that, I'd like to go back to Teo, because that's exactly where your work comes in, right? Because you work on AI, and how can AI help us, with creating a new battery, better battery right now today?
Absolutely. Before I jump into the AI topic, there is one thing that I wanted to comment on what mentioned by Gavin. It's a very exciting field because to a certain extent we are experimenting exactly what quantum chemistry was experimenting 30 years ago, when we still didn't have the computational power that we have today. And so we are really trying to adapt algorithms and grow and adapt the algorithms with the growth of the corresponding hardware. I think it couldn't be a more exciting time for people that are developing software, for people that are thinking how to apply the physical schemes on hardware. So it's really a very fascinating time. And now, following on your question, AI, of course, we start from a different perspective, the perspective of the data. And I think, I'm actually here in the lab, and I'm apologizing for all the people that are listening if there is a little bit of background noise. It's truly live with operations in the autonomous lab. But the AI is really, in the last years, really got a very important role in the space of material design. We have been using AI for collecting information. We have been using AI for building models that were capable of predicting new materials hypotheses. That's at the end is one of the main advantage of machine learning and data-driven models. Reasoning on data, extracting patterns for data, identifying correlation, and using those signals to support the domain expert in producing new type of materials for battery application. AI is also doing something else, though, and that's really very important. It helps us in synthesizing those materials. And that's the reason why I'm here today. The space where I'm broadcasting from is actually the first autonomous lab connected in the cloud, reachable through internet. It's really an embodiment, a chemical laboratory embodied in the cloud. So Having said that, we really talked a little bit about the use of AI in the technology stack. And AI is really helping to accelerate a different stage of the research. And this is what we actually in IBM call accelerated discovery. We are taking big advantage of AI, but also of quantum and cloud, different type of technologies to accelerate the research and be able to design new materials with a 10x factors on time and cost. So this is really the objective of the accelerated discovery. Reduce as much as possible the trial and error to be able to design new materials, better materials, faster and with a more precise specification on possible usage.
Mm-hmm. Mm-hmm.
There is another space that I believe a little bit more disconnected from AI. It's a little bit more general, and I think that will be another sector where we will be observing a lot the use of AI. I think in mostly all modern electric vehicles, there are systems of artificial intelligence for managing the battery packs. So that's really very important. I mean, real-time data analysis of all the sensors that are in that battery packs that really allow to calibrate the use of the pack and again improve the experience for the people. So AI is having a humongous role for what is basically most relevant for me, for us that are talking about research in the design of new materials, but it will have really incredible implication on how complex battery infrastructure are going to be easily handled in the future. It's very similar, if I can make a last parallelism, to the fly-by-wire concept. Why did people introduce the fly-by-wire? Because there is a lot of complexity in handling unstable design of aircraft, and you really need to rely completely on computer. And here in this case, whenever you start putting together different battery packs, so we are talking about technology, but we are talking also about all the package that is taking care of the cooling of the battery, how much power you can drain out of the battery, and how much power you can even inject in the battery, the system starts to be incredibly complex. And of course, it's beyond the human capabilities to handle that complexity, and it's there where AI can come and help.
Mm-hmm. Right, right. Well, so you kind of mentioned that you're in your AI lab right now, but I think what you haven't done yet is actually named the machine that's doing all this amazing work, right? You're next to it, aren't you? So maybe you could introduce us to your robotic helper there and what it does exactly.
Absolutely, it's really a pleasure. So the environment that you see behind me is actually what we label Robo RXN. Robo RXN itself is not something physical. It's really a blending of three technologies. We have AI, we have cloud, and we have commercial automation hardware. Behind me, you can see the third component, the commercial automation hardware, together with analytical instruments here on my left. So Robo RXN was really the extension of the work that we did and that we named in 2018 IBM RXN for Chemistry. Is the primary goal of that activity is the extension, the use of natural language processing technologies to domain-specific languages, and in our case, chemistry. So we have been really demonstrating like you can use the same architecture that we routinely daily use for translating between English and Spanish or Italian or Japanese, and use exactly the same technology, train those architecture with chemical data to support the chemist in design synthesis, in synthesizing new materials. And in this lab, we are strongly specialized on small organic molecules. And while most of the battery application is actually solid state, so we are not really talking talking about organic molecules. Here, instead, we can design and synthesize molecules that can really make a difference for energy storage device like electrochemical flow cells that are very relevant and very important for large-scale application. So it's possible to synthesize materials that molecules that have specific redox potential, and then optimize the difference in redox potential in such a way to maximize the output voltage of the entire technology. And here I think we are streaming some of the images out of a sample of a chemical synthesis that we have been doing for one of these small molecules in the context of semiconductors, but the images are pretty similar. So very interesting technology. Again, even if highly tailored for small organic molecules, but very relevant even for optimizing large-scale energy storage devices that may have a very relevant application for the grid.
Mm-hmm. Yeah, I remember you not so long ago. You even created a molecule live in front of a live audience, right? At the shore of the Zurich Lake. So, if people want to watch Teo do that, so Google something like Teo IBM Research Molecule Live, and I'm sure you'll come across the YouTube video. And it was quite a show. It was quite amazing.
Absolutely, Katya. It was the time we were streaming by the Lake of Zurich. This time I decided to stream from the lab. It's really the final concept of providing even to chemists an home office opportunity. You can do chemistry from the sofa and the comfort of your apartment.
Yeah, absolutely. Before we go to the questions from the audience, there are quite a few that are waiting now. I'd like to ask you, Gavin, actually, what your thoughts are on Robo RXN and specifically like on AI more generally. Actually, how do you think in the future quantum computing can help, or actually not help, but work alongside AI to together these two technologies kind of accelerate our research of new materials for batteries even more? What do you think?
Yeah, sure. So first of all, I think Robo RXN is very cool. I'm a trained chemist, and I actually think that a lot of that I see in AI and machine learning, especially for chemistry, is almost like magic. I know a lot of my experimental chemistry colleagues at Almaden, where I work, were very excited to see the Robo RXN demonstration and what it could mean for their research. And it was exciting for me as well. I think a lot of my experimental chemistry colleagues were excited about the fact that they could actually, as Tia said, actually do experiments from home. So, which is perfect for the current times that we're in, right? But talking about the combination of AI and quantum computing, actually, we've already started to make progress on uniting quantum computing and machine learning for investigations of materials. In particular, we deployed quantum machine learning to assist classical DFT methods in a study of disordered crystalline materials used in lithium-ion batteries. We've also used neural networks to improve the precision of observables for chemical systems to arrive at more accurate results. So these examples highlight the pathways that one could take when leveraging AI and quantum computing for chemistry. So using machine learning to improve quantum algorithms, or using quantum machine learning to improve on classical results.
Right. Well, here's a question for you, Gavin, from the audience here. I don't have the name this time. I'm sure you all are not the only ones researching the use of quantum and AI for applications on batteries. Really? Well, I hope you're not. Anyway, do you have any stories of how you learn, you collaborate with other researchers on this topic? That's a good question.
Certainly. So we actually work with partners. So so at IBM we don't go. We're not on this path alone. We work with a number of partners, and typically what we depend on from these partners is that they come in with the subject matter expertise. So they're the ones who are coming in with projects and saying, hey, how can we actually use quantum computing to study this type of material or this type of system? And so we've partnered with companies like Daimler, Mercedes-Benz, as well as K University, JSR, well, K University is a university, of course, JSR, Mitsubishi Chemicals, to actually study these types of systems. And typically they come in with a use case, and then we try to help them tailor what they're interested in to the quantum computer.
Mm-hmm. And can you share any of the latest results maybe with any of these companies? I mean, how close are we to applications really?
Oh, sure. Yeah. So we have, as I mentioned, we worked with Daimler Mercedes-Benz actually on the project that I mentioned earlier, using QML for study of lithium-ion crystalline materials, and we've also worked with them on lithium-sulfur batteries. We've also collaborated with Mitsubishi Chemical and K University, located in Japan, on the research involving lithium O2 batteries, where there we were looking at a reaction that's proposed to occur in lithium air batteries. Of course, we're also working with other partners on other topics in chemistry and physics. For example, we worked with Mitsubishi Chemical, K University, and JSR on simulations of materials for OLED applications. So we believe that partnerships like these are very valuable, as I mentioned, because the partner comes in with the subject matter expertise and challenges us to actually be able to study these systems on quantum computers.
Mm-hmm, mm-hmm. And so you mentioned lithium. So basically, I guess my question is, are you mostly trying to kind of improve the current lithium-ion batteries, or are you trying to move away from lithium-ion completely and create something completely new?
We're trying to do everything basically. That is of course our goal. That's the goal of research, right? Is to be able to improve the things that we have now, as well as to actually look at some new areas that could potentially offer us a new pathway or new technologies that we can actually iterate on and can actually improve the things that we're working on right now.
Right. And Theo, what do you think about lithium-ion? Like, what's wrong with current lithium-ion batteries right now? Anyway.
Yeah, let me also follow up first. I mean, on the question that was coming from the audience. There, beyond, I mean, the very relevant, very important collaboration with industrial partner. We also have stories within governmental funded projects. So an example here in Switzerland, for people that may be aware of that, is the Marvel Center for Research, basically, where we have been really using in the last 7 years AI resources and technology to design new cathode materials, new anode materials within a specific type of technology. So I think it's a very interesting. I'm sure. I mean, beyond even the one that I'm mentioning, if we go across the entire research unit, we will find very amazing stories of collaboration in the space of batteries. As I said, it's really a 10 years plus belief that we have in novel materials that can change the landscape of storage devices. And why do we need to do that? Let me connect to your question about lithium technology. There is nothing really bad about lithium. In reality, we have a very solid network of recycling for lithium. However, I mean, the current trend, the current extrapolation, if we really extrapolate to an entire humanity relying on electrical energy storage devices, one of the main concerns is really availability of lithium. And so it's really important to explore different type of technologies. There will never be one battery that fits all type of problem and all type of application. This is something that we will have really to uh, to uh, to realize and live with that. We were discussing, Katya, initially about battery for grid application. These type of batteries are completely different from the batteries that are running an electric vehicle. In an electric vehicles, we want to have reusability, we want to have rechargeability, and we want to have even a larger number of cycles. Now, to a certain extent, lithium technology made it really possible. It made it possible in terms of gravimetric energy density, and this basically means with the same weight, we are carrying an amount of energy that, even if less than the one that a liter of gasoline may be producing, is still pretty much comparable in the overall economy of the energy conversion in a piston engine. But there are other technologies. I mean, we have been looking at sodium. We have been looking at other metals, providing the source, the main energetic drive. I think it will be important to have a specific differentiation where we are really identifying different technologies for the specific use, and different technology and different type of materials for the specific use. And there, the importance of using AI, the importance of using quantum for calibrating, optimizing the material design, quite often can make a big difference in terms of several equivalents of megawatt hours of energy that are stored in a device.
Yeah, sure.
So I'd like to just interject here. So yeah, first of all, yes, I agree with Theo. So some of the other some important reasons, as some of them that Theo mentioned, is of course abundance of lithium as a natural resource. There's a finite amount of lithium available. It's worthwhile to look for an alternative battery material. For example, sodium, as Theo mentioned, is widely abundant. It's a lot cheaper. Moreover, in some cases, the technology used for lithium batteries rely on other natural resources, for example, cobalt, which are obtained in problematic ways. So they're in conflict zones, for example. And if we can create batteries that don't rely on such materials, then it would be better for us all, I believe. There's also a possibility of creating safer batteries. So safety is also another important concern here as well.
Yeah, for sure. I totally agree. And actually, important question here from the audience, which we probably should have addressed a little bit earlier, but better late than never. H. Lander is asking, what actually describes the battery of the future? And is it just an accumulator, so reloadable, or just a battery that is like gone after draining? So what's your view?
I'll pass it over to Theo. What do you, I don't know if
Absolutely.
you have.
No, I want to remark what I said before. There is not going to be the battery of the future. There are going to be batteries of the future. What we need to do, and this is the responsibility of science and research, is really push all the technology to the level where we are really achieving a very high level of gain in terms of energy stored and very little losses. So I was thinking when Katya, you were reading this question, I don't know why, it came to my mind the thermonuclear batteries that we use in satellites. This type of batteries, or in rover that are exploring other planets on behalf of humans. These batteries are going to be there, and because they offer a certain number of reliability and independence that different type of technologies are not really capable of offering. But this is really only one example. We will have battery that will be specifically optimized for electrical mobility. We will have battery that will be optimized for grid application, where actually there is not too much pressure and stress on the number of cycles that you can achieve. Because normally when you talk about batteries for mitigating the grid or absorbing a surplus of energy produced by renewable sources, you should really picture like huge containers, thousands and thousands of liters of solutions. These are the electrochemical flow cells, where you are actually storing the excess energy, and whenever needed, this is actually released. But you are not doing the same type of use that you do with batteries and electrical mobility, where maybe you are charging today, discharging in 3 hours, and then recharging again in 4 hours. So there will not be one battery, but there will be many batteries. And I think our role is really the one of being sure and that the technology like AI and quantum are really used for improving the design of the material storage technology.
Yeah, for sure. And of course, as you mentioned, I mean, storage is super important for renewables, right? Because obviously, when we've got solar panels or wind turbines, you're not gonna, like, we do have to store that energy for longer, even during the night or when there's no wind, right? So we shouldn't be dependent on the weather conditions, and we are right now. So so that's all super important. I totally agree. Here is a question from Akhil Kara for Gavin, I guess. And Akhil is saying, are there any new tools under development, especially with respect to quantum computing, that will help simplify and speed up quantum chemistry and computational chemistry research?
Yes, that's a good question. At IBM, we're always trying to make the tools that we're using and the tools that what we're offering to the wider public as to make it as easy for users as possible. And yes, so we're always trying to make improvements to the main software that we use, which is called Qiskit, so that a lot of it that users are exposed to, like application researchers are exposed to, will be abstracted away from the user. Also, if you are interested in, say, not only working on applications in quantum computers, say to improve battery research or so on, then you could also look at things like if you're interested in, say, making better qubits, then you could look at Qiskit Metal. So we have a lot of tools that we're trying to actually implement that will make things easier for users to actually use the tools that we have.
Mm-hmm, mm-hmm. Great. Yeah, absolutely. Thanks for that, Gavin. And here is a question about recycling from the audience here, which is actually a really important aspect as well that we haven't really talked about much yet. So Charles Guo is asking, is there any fundamental change of batteries technology? What about recycling? How to save the weight in order to use battery in aviation industry? So I guess it's several questions in one, but Theo, maybe you could talk to us about recycling specifically for now, and then address aviation.
This question is just touching me on my most interest, which is not recycling but aviation, actually. So
of course, because you fly, right? You're a pilot.
Absolutely, right? Absolutely. Exactly. So let's first start addressing a fundamental change of battery technologies. There have been in the last 10 years a very I would say important attention by many companies, including us, to metal air technologies. I would really say that these technologies, at least on paper, it's actually the one that can deliver an incredibly competitive gravimetric, and I'm always referring to weight for a reason. I'm arriving there compared to the fuel that we are burning in piston engine. There are some difficulties, however, and this is more or less where I personally, from my perspective, I really left the field of metal air batteries. One of the side products in this process is really the formation of substances that are highly oxidizing. We are talking about peroxides, superoxides, and the reason is that one element is the metal that you are carrying with you, but the other element is the oxygen that is in the air. And that's the beauty of this concept. You don't need to care the anode and the cathode, actually, or the anode and the cathode material, but one of the two, the oxygen that is in the air, is directly available, and doesn't really contribute to the weight that you are carrying. There are, however, as I said, important challenges, and one of those that we have been looking for several years in a period where AI was not yet there, unfortunately, was the stability of the electrolytes. You always need a medium for diffusing the ion and closing the cell. Most of the electrolytes are organic molecules. And one of the main complexity was really to identify stable electrolytes that may have undergo to a specific number of cycles. In general, for use application, we are talking about several hundreds, if not 1,000 cycles during the time of the battery without really degrading. And this, unfortunately, didn't really happen. And I think there is always a lot of research. The interest for metal oxygen batteries, of course, is shifting towards solid state concept. So you are completely getting rid of the organic electrolytes to have instead the presence of a solid state electrolyte with huge benefits in terms of chemical and electrochemical stability. So these are some of the, I would say, forefront technologies. Nothing that, unfortunately, we will be able to consume tomorrow, maybe in a few years. It's always the big question mark, are we going to make that technological discovery that is going suddenly to make the entire technology usable? In the lab, metal air batteries are amazing and are one of the still well thought and always considered ideas to promote mobility in aviation, so electrical aviation. And there we are going into the second part of the question. What do we really need? Well, we need light batteries. We need really batteries that are competitive in terms of gravimetric and volumetric energy density in an airplane. It's important also the volumetric components, because the wings, which is normally where we are storing fuel, the wings of the airplane have a fixed volume. So you want to maximize also the volumetric density. Normally with the design of the cars, the volumetric density is important, but you can always play a little bit increasing the volume of the car, making a car a little bit bigger, and the stronger focus is really on gravimetric density. In the case of airplanes, instead, the two are playing, both of them, a very important role. One, because the volume is normally pretty well defined, and the second, because the weight is going to have a very important component. If you are too heavy, you are not taking off from a runway. In all that, and I will close it here, recycling. It's an important component of every battery technology. We are talking a lot about sustainable goals. But when we talk about sustainable goals, it also means that all these technologies that are not necessarily, renewable in principle, because we are taking resources, land resources, we are taking lithium, we are taking other minerals for building the batteries. We have to act in a very responsible way. And the amazing things for lithium-ion batteries is that after roughly 30 years of consumer consumption by the people, we have in place, I don't have really the last digits of my availability, but we have in place a mechanism, a chain of recycling that can actually recycle more than 95, 97% of the batteries. That's really where we have to aim, and ideally even push the number higher.
Are we working on any of that? Somebody is actually asking whether you guys are doing any research that could lead to more kind of easily recyclable batteries.
So regarding recyclability, one of the main components beyond the material itself is really defining the performance, the electrochemical performance. But the recyclability and how easy it is to recycle is really a packaging problem. Normally is an engineering problem. And it's there that AI comes to our hands. We have some projects that we are incubating inside our research lab, where we are using AI to drive the design of packaging and user product. Not only the design of the materials, the chemical composition or the formulation, but really how you should assemble your consumer goods in order to maximize specific properties. This is a very interesting concept for AI-aided design of products in semiconductor industry, but also in the energy storage domain.
Yeah, fantastic. Thank you for that, Theo. And just a very last question here, probably very short, but important for the audience. Somebody is asking where they can actually go and experiment with quantum computers today and with Robo RXN. So if you guys can point our viewers here to the right direction to play around with Qiskit. And I don't know if it's possible to do anything with Robo RXN, but let us know. Gavin?
Sure, yeah. So as I mentioned, the IBM computers are accessible through the cloud. If you go to quantumcomputing.ibm.com today, you can sign up for an account. You can start playing around with IBM quantum computers. You can start learning more about quantum computing. And so this is a resource that is open for everyone, and everyone can use it today.
Fantastic.
And I want to stress the appeal for Qiskit, also an appeal to all the quantum chemistry or computational chemistry that are in the audience. Take the initiative and start really experimenting with the early technology. Early quantum computing technology is going to be an incredible investment also for career prospects. I mean, we should learn by the history. And as I said at the beginning, this period is resembling a lot what I experienced only partially at the beginning of the 90s. So fantastic era. Regarding Robo RXN and RXN, all the models, we make available all the models. So if there are people that are interested in chemistry, synthetic chemistry, how can you predict the outcome of a chemical reaction? Are you preparing yourself for chemistry classes? Reach out, IBM RXN for chemistry. Just Google and you will land on the website, and you can use the resources, the train model for prepping your chemistry class exam. Thank you.
Fantastic. Thank you so much, Theo, and thank you, Gavin. That was a fantastic session. I hope our viewers enjoyed it as much as I did. And thank you to everyone for joining us today, of course, and to our stellar team of scientists behind the scenes that were answering questions in the chat. And if you guys have any comments, ideas, questions, you can always find me, for example, on Twitter, and send me a question or whatever you like, DM me. And please don't forget to subscribe to our channel and join us again next month. Thank you and goodbye.
Thank you. Bye-bye.